So the way it is typically written, if I take, so again this is the expression to keep in mind over here. Slope means phi prime alpha, right. So phi prime alpha is this. Now for small values of alpha, this slope is negative, right, because it's a descent direction, right. So let's just note that down. Since pk is a descent direction, phi prime alpha is less than 0 for small alpha. I know this, right. So if I want to put a condition on the slope, I obviously this is the first thing that I have. This is the slope, but it is less than 0 for small values of alpha. So if I want to make it a positive quantity, what should I do? Multiply by minus. This is the slope in terms of a positive number. This should be less than C2 times the slope of the linear approximation, right. Now slope of the linear approximation again is going to be written as, let me write it over here first like this. So minus grad f xk transpose pk multiplied by C2. C2 is our relaxation, right. So this is the, you can think of this as mod of slope at alpha, and you can think of this expression over here, at least this part over here, mod of slope at 0, right. Now so do you foresee a problem? I mean, this is heading in the right direction, but do you see a problem over here with this expression that we have when we wrote it down like this? So let me make it a little bit more specific. What happens when alpha goes past the stationary point? So look at this graph over here. Where is the stationary point? There is one over here and there is one over here, okay. So let us say I started from the leftmost part and I am increasing alpha. Once I go past the first stationary point, what happens to the sign of phi prime alpha? Phi prime alpha has to change a sign, right. So if I keep this condition as it is, this quantity over here, what is its sign? For any value of alpha, what is the sign? It does not depend on alpha, first of all. Second of all, what is its sign? The entire expression, it is positive. This is always greater than equal to 0, always. On the other hand over here, when I go past, so for small alpha, this is greater than equal to 0, and that is when this inequality made sense. The moment I go past a stationary point, what happened? This flipped sign, right. So past alpha star, let us say, this became less than or equal to 0. If this became less than or equal to 0, is there any problem in satisfying this inequality? Right, I have minus 100 on the left hand side is less than or equal to, let us say, plus 50. There will never be a problem with this. Is that good or bad? It is bad because it is allowing me to overshoot. There is no arrestor mechanism to prevent it from really going across over there, which is why the only point at which it would get arrested is when it goes past this point. Once it goes past this point, then it is negative, and so therefore the left hand side is positive, and then this inequality can get reversed, right. So this condition as it is stated is called the, it is just as I mentioned, called the curvature condition, okay. If you wanted, you could eliminate the minus signs, that would just simply flip the inequality. But we found a problem over here that allows overshooting. Right. So if you were in charge of affairs over here, how would you fix this problem? put a, so you want to replace that by 0. One more inequality on the left of equal to 0. So, okay, that is one solution.
So actually, in this condition itself, it's satisfied. Right? Like the written as intuition, mod 5.
Correct. So, he is right. Actually, our intuition was correct. Our intuition put a mod over there. We messed it up. I mean, Wolfe kind of messed it up when he wrote it out explicitly with the minus signs, right? So, if you put a mod over there, you get what is called the, it has another name, it's called the strong Wolfe condition. Actually, it's very intuitive, it sounds fancy, but there's nothing too different about it, which is a strong Wolfe condition. Okay, which simply says that now put a mod sign over here. Okay. Typically what is done is that your C2 is a little bit larger than C1, okay, typically. But having done this, so this is fine. I mean, this intuitively we understand that we don't overshoot too much. But can we try to plot where this is going to happen? So with the regular Wolfe condition, I have this entire, you can say, orange range of alphas are allowed. Okay. Now when I put in the mod, where else will this get, is this range reduced? That was the whole intuition. We wanted to prevent overshooting. So now is the range going to be reduced? It is. So how do I construct this reduced range? When will the mod of phi prime alpha be equal? Mirror image. Okay, anything else? Not mirror, he is right. It's not mirror, it's something related to mirror. Basically, we have to find a place where phi dash at this new point is negative of phi dash at this point, right? So, if two slopes are related by a minus sign, what is their geometrical relation? Okay, whatever it is, let us say it is something like this. At this point, the slope is minus times slope here and slope here, right? These two have a relation of minus 1, right? So, when I start with alpha equal to 0, it is found to be too small because of the curvature condition. So, I keep, let us say, increasing alpha, right? Then I enter into the acceptable range and I keep increasing, and once I go past this point over here, the magnitude of the slope now increases, right? Now the slope is getting like this, right? So, I reject it. So, I stop over here. So, now this is my, with the strong Wolfe condition, I am making sure that I don't overshoot too much, and at least in this graph you can see that I have bracketed my solution. Question?
We will have some region around the maxima as well.
Not necessarily, no. At the maxima, what is happening? Phi dash is actually 0. So, okay, let us start from the point of minima. At the point of minima, phi dash alpha is 0. It starts increasing, and then at some point it has to stop increasing to go to 0. Right. So, first it has to increase in magnitude and then it will decrease.
Yeah, this means like there will be some region around the maxima, right? Which will like qualify.
But the point is that before it reaches the maxima, I will exceed this condition. So, it's very good in preventing me from going past the second maxima. This entire discussion is pointless if I have a convex function, right? For a convex function, once I find this one, even I think even the regular Wolfe condition with some fixes will work, but in this case the strong Wolfe condition is very useful in just bracketing this. So, I will suggest just working with this, the graph the way I have drawn it and drawing slopes this way and all, and convincing yourselves that alpha, if I pick it this way, if I use the strong Wolfe condition, what have I achieved? First thing is very small values of alpha are rejected. That was clear. Second is I can choose a biggish step now and I prevent overshooting. Right. So this is put together, this is probably the most effective of conditions. Right. What is the cost that I have to pay to implement the strong Wolfe condition? By cost I mean computational resources. Yes, question? Yeah. Putting the mods. Yeah.
What if you overshot but you couldn't identify the one with the modeling? What if the slope does not increase to that extent?
The slope is starting from 0. Oh, you are saying if the function has a very weak value.
Yeah, very weak.
If you have a very weak value, too bad. I mean, so that is a problem with functions with very flat curvature, that convergence becomes very slow, and there are separate methods to deal with that. More aggressive line search strategies are there, right? But that is in general a problem all methods will have. If once you enter into the region of a minima, but the curvature is very flat, then convergence is bound to be slow. So that we will deal with another set of techniques. The point here is to prevent an overshoot past another local maxima, which is being prevented over here.
So how are we getting the alpha in this?
We haven't. So far I have not told you how to get alpha. I am just telling you ways to put brackets on what are the ranges of alpha that we should consider. We will talk about how to choose alpha soon, in a few minutes. That I have not told you yet.
So which means in addition to that condition, strong Wolfe condition, we should also have one more condition on the double derivative, right? Because there could be a region around the maximum which will still satisfy.
Okay, so that's a good question. Why don't we start invoking second derivative information, right? Computational cost is going to be very high, because now so supposing I give you an algorithm and that algorithm has to check whether or not this alpha is good enough. That means that each check, that was my original question, what is the computational cost? Evaluating phi dash alpha. Only once you evaluate phi dash alpha, can you verify whether or not this is true. Right hand side is given and fixed. At alpha equal to 0, I know phi is 0, phi dash 0 is known to me, C2 is a prefixed number. Right hand side is fixed. Every time I go pick some alpha, I have to substitute over here, calculate phi dash alpha, is it good enough, yes or no. Depending on that the algorithm proceeds. So every time if I have to evaluate phi dash alpha, which for a realistic problem may be difficult. Okay. So actually it's good you mentioned this. For a realistic problem, how do you think I will calculate phi dash alpha? It's unlike the example which I gave you, no real life problem will have phi of alpha equal to sine multiplied by cosine multiplied by log multiplied by tan. It's going to come from where? Data is going to give sort of in many cases give you what this function is, and you will construct some model, maybe a linear model, quadratic model, right? So the function is not going to be given to you, you are going to be given data, right, of it. So now how do I calculate phi dash alpha, or in general how do I calculate grad f? I mean, we have all studied this in class 11 and 12, that's the hint. Take 2 points and then take the function value, take the difference. What is there a nice name for this technique? Rate of change, okay. Finite difference, right? So df by dx1 was equal to what? F of x1 plus epsilon minus f of x1 divided by epsilon, and of course limit epsilon tends to 0. On a computer I can evaluate this very easily. I mean, not very easily, but I know how to do it. I need to know x1, I need to know x1 plus epsilon, evaluate the function at that point, take the difference, right? So this is called finite difference. So if I have a function that is living in n dimensional space, how many function evaluations will I need to do in order for you to get this guy? Is it n? I mean, it's definitely order n, but we can be a little bit more precise. No? It's n dimensions. I need to calculate n partial derivatives. How many function values do I need to calculate? N plus 1, because the point over here is fixed. I need to make epsilon steps in each dimension, right? So, for example, if this were 3-dimensional space and I have a function in 3 variables, I need to know the function value here, 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 here. Then I can calculate finite difference in each direction, but that one guy is common, which is f at the origin, and f at origin plus epsilon in one direction plus epsilon. There are n such directions, so there are n function evaluations that are separate, and one guy sitting at the origin, so n plus 1, but we can say order n, right? So calculating gradient is not easy. You should be willing to invest n plus 1 function evaluations. So going back to the antenna example, if your function took 4 hours to evaluate, right? So you better be careful if you are asking for a gradient evaluation. So I guess I don't need to scare you with second order calculation, right? Second order can also be calculated again by finite differences. So the number of function evals will just keep increasing to the point where most practical implementations of line search methods, where you are hunting for an alpha, will say, okay, let's stop at linear, okay, because this trade-off is too much. There is one, I mean, there are a lot of tricks that we can play. If I have n cores on my processor, I can parallelize this operation, because function evaluations can be evaluated in parallel, right? So you could distribute this on different cores and get the answer back much faster. So these are, again, then as you go further into this, these are the things that you have to keep in mind. How many cores are there on in my computing architecture? How can I parallelize this and so on, right? So